I'm John Gille. I'm at the University of Colorado in Boulder and also at the National Center for Atmospheric Research in Boulder. I'm the NCAR. I'm a senior scientist and EOS program manager, and at the University of Colorado I'm a senior research associate and also adjunct professor of atmospheric and oceanic physics.
Would you talk about the definition of the limb and the importance of limb scanning in remote sensing?
Well, the limb is an astronomical term that means the edge of the planet or the edge of a star or the sun. And in limb scanning, we scan up and down across the horizon as seen from the spacecraft, measure the infrared emission coming from the atmosphere at the limb. And the benefits of that are you have very long paths through the atmosphere, which give you sensitivity to go to high altitudes, and you can see species that are present in very small concentrations. And also, you have a black background, so all the information is coming from what you want to look at. And most of all, most important, you have very good vertical resolution in your weighting functions. So you can see things in the order of a couple kilometers or less deep. And I think that's one of the things that really makes it extremely attractive, especially for looking at regions around the top of the troposphere or the base of the stratosphere. That's the region, the boundary between those regions is called the tropopause, and things happen rapidly there. And so the high vertical resolution you really need to pick out what's going on. And so that's one of the reasons we employed limb scanning, and that was one of the main emphases of the HIRDLS mission.
Please describe the HIRDLS experiment and what types of observations were expected.
Well, the HIRDLS experiment was a 21-channel infrared limb scanner. The goal was to obtain measurements of temperature, ozone, water vapor, and 8 other trace gases from about 8 kilometer altitude up to 80 kilometers from pole to pole, and provide much more information about that part of the atmosphere.
And can you describe the problem with the instrument and how it was addressed?
Well, at launch, a piece of plastic that was part of the inner lining of the optical cavity came loose and fell across the scan mirror and covered something like 80% of the aperture, between 80 and 95% of the aperture, depending on which channel you're talking about. And it also covered the view to our in-flight calibrator. So it cut off our ability to calibrate the way we expected, as well as providing this blockage, which cut down our view and also put a lot of extra signal into our detectors that wasn't coming from the atmosphere.
How did you manage to get the most out of the compromised system?
Well, these were things and ideas that evolved from quite a number of us over a period of time. But we essentially broke it down into four main problems that we had to deal with. One, as I mentioned, was the calibration. We solved that because we had calibrated very well in the laboratory, we were able to run our detectors at the same temperature, assume the gains were the same, and we were able to parameterize what our space view should have been, and that has seemed to work quite well. When the scan mirror does its vertical scan to scan across the limb, it also causes oscillations in this blockage, but fortunately those are very monochromatic, so we were able to filter those out and use a set of empirical orthogonal functions to remove them from the radiances. Determining the fraction of the area that was open has been tricky, but by modeling the what is contributing to the variation of the signal that we see as you go around the orbit. We've been able to, and looking first where we're seeing only this blockage, and secondly where we're seeing partly to space, looking at that difference, we can pull that out. The most difficult has been removing the variable signal that's coming from the blockage, and that's we've developed a set of empirical orthogonal functions. It works pretty well, but it doesn't get down to the very, it leaves some errors that are large enough that we are having difficulty getting some of the constituents, some of the trace gases whose signals are low, methane and water vapor being two good examples.
The story of the HIRDLS problem is one of overcoming adversity with innovation. How prepared can you be for realities like this, and how did the innovations develop?
Well, I don't think you can be prepared for any specific thing, because there are so many different ways that things can go wrong. Some things work and you're very happy, and other things, facts shoot down beautiful theories and you have to start over. But I think the main thing is to not think in a box, but think broadly, look at the whole problem, try and see what are the possibilities, and check a lot of things out.